So sampling distribution, a distribution that we can make up, a probability distribution that we will make up using the samples that we have picked from a population or using the sample statistic can be considered as a sampling distribution. This kind of distribution forms when the samples of n are repeatedly taken from a population. Okay, let us see an example. The sampling distribution of sample means if the entire rectangle has a population with a mean and the standard deviation, you can see the different samples that we can pick from the population data and the sampling distribution. So each and every, this x1 bar represents the mean of this sample 1, x2 bar represents the mean of sample 2, x3 bar represents the mean of sample 3, and so on. Okay, so this, if you make a distribution of all these stuff, okay, then that distribution can be called a sampling distribution. Okay. Here in this distribution that we can call the standard deviation as the standard error of the mean. Okay, remember this one, standard error of the mean. So sigma is equal to mu represents the mu same, mean is same, whereas the standard deviation of the sample represents the sigma divided by root n. Okay, square root of sample size. How much, what is the size of the sample? It is not the total number of values. Otherwise, total number of samples that we can say. So now, the population values you can identify 1357, okay, which are completely written on the slips of the paper and put it in a box. 2 slips of the paper are randomly selected with replacement. This is not without replacement, this is with replacement. So guys, can you please tell me how many population values are there here? 4. We have 4 population values, 1, 3, 5, 7. 1, 3, 5, 7. Totally 4 population values. Okay. If I want to take the mean, 1 plus 3 plus 5 plus 7 divided by 4. Okay. We'll get 4. Variance. How do you identify the variance? Sum of square difference. Average of square difference of scores from the mean. Okay, it was implemented in the same way, and the standard deviation is 2.236. okay, but if I'm going to take a sample out of this, okay, remember the mean is 4 and variance or standard deviation is 2.236. I just wanted to take some samples of size 2. Okay, one sample represents 1, 3. Another sample represents 1, 5 or 3, 5 or 3, 7 or 5, 7, something like that. Take a look at this one. The graph probability distribution for the population values. 1 time I have taken. 3 one time I have taken. So the the probability of picking up each and every value from the population of X will have 0.25. which is 1 divided by 4. 1 divided by 4 represents 0.25. Okay, which will comes as a uniform distribution, uniform probability distribution. Here you can see I have listed all the possible samples of size n is equal to 2, and I have tried to calculate the mean of each sample. 1, 1, 1, 3, 1, 5, 1, 7. That's the combination. 3, 1, 3, 3, 3, 5, 3, 7. So in that way, I'm going to get all the mean values. Okay. And all the mean values, how many in number that I have got? You can take a look at this one. I have got 4 times. Okay, I've got 7 one time. Something like this. If you try identifying the probability, you will get this probability. And if I'm going to graph this probability distribution, this is how mean will become same. Okay, this is a sampling distribution I'm talking about. Whereas sigma square, which is a variance, sigma divided by n is equal to number of samples, size of the sample, which is 2.5. Sigma standard deviation is equal to root of 2.5, which is going to be 1.581. Okay, so if you take a distribution of all the entire stuff, the graphing up the entire probability histogram for the sampling distribution of the sample means will come something like this: 1 comma 2 comma 3 comma, something like this. It's almost like a bell-shaped curve or a symmetric curve, which approximates to a normal distribution. Are you all good with this one so far? So here comes the central limit theorem. When you have the samples, see, till now so far we don't have any theorems. Here we have something called a central limit theorem. Okay, why? Because of the samples, because of the introduction of the samples over here. Okay, because of introducing the samples over here, if samples of size n greater than 30 or n greater than or equal to 30 are drawn from any population with the mean is equal to mu and standard deviation is equal to sigma, maybe the resultant graph represents something like that, then we will make that sampling distribution of the sample means approximate to the normal distribution. Okay, when you have the greater the sample size, the better the approximation. Understand? So when you have the sample sizes greater than 30, you can always be eligible in order to approximate your distribution to a normal distribution. If it is less than 30, okay, if it is less than 30, you cannot try doing the normal distribution. Okay, if the population itself is normally distributed, the sampling distribution of the sample means is normally distributed anyhow. That is for sure. Okay, in either case, the sampling distribution of the sample means has a mean equal to the population mean, whereas the standard deviation will be little bit different, where sigma is equal to sigma divided by root n. So you can see the understanding here. Any population distribution which is greater than the sample size which is greater than or equal to 30, you can approximate to standard normal distribution. Okay, standard distribution. Okay, a normal distribution. See, the given distribution itself, a normal population distribution, out of which you are trying to take some sample means or sample something. Okay, obviously by default you will have the distribution of the sample means in a normal distribution mode. Okay, all of you understand? All of you? Okay, if you don't understand, please let me know. Are you all good with this? Okay, so I'm repeating one more time. Central limit theorem deals with the size of the sample. Okay, why? Because we are dealing with the sampling distributions. When we are dealing with the sampling distribution, then only we have to concentrate on the curve and how we can approximate to normal distribution. Okay, so when your population distribution is something like this, okay, when your population distribution is something like this, okay, when you're taking the samples and when you're taking the sample size of which is greater than or equal to 30, the researchers have told that you can go ahead with the standard. You can approximate your sample distribution to a normal distribution of the curve. Okay, you can make an approximation to the normal distribution. Okay, if it is less than 30, can you do it? No. If it is less than 30, you can't do it. You can do it only if your sample size is greater than 30. What if it is less than 30? That's a different scenario. I will explain you. Okay, for example, if your data itself is representing the normal distribution, normal population distribution, by default your distribution will become the normal distribution. Okay, for all the sample means whatever that you're going to take, you can approximate to the normal distribution. Okay, so now here we have the um, example. Phone bills for residents of a city have a mean of $64 and standard deviation of $9. Random samples of 36 phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and the standard error of the mean of the sampling distribution. How many random samples have been taken? Huh? Tell me. How many random samples have been taken? How many sample? What is the size of the sample? So size of the sample is greater than 36. Okay, if you can take a look at this one, if you can take a look at the distribution of all the phone bills, which is a population data, is the population data looking something like a normal distribution or not? Hmm? Is the population data looking like a normal distribution or not? Where it is looking like a normal distribution, tell me. This is completely curvy in nature, right? It is looking like a mountain. Actually, it is not even in a, see, you know how a normal distribution looks like, right or wrong? The bell curve is different from what you are seeing here, right? Are you with me? I'm not talking about the sample 36. Let us forget about it. I'm talking about the population data which is representing in the problem. Sample is different. Population data is different. Taking sampling out of the population data is different. In the given problem, the fellow mentioned here the population distribution graph. You just tell me, is the population distribution graph looking like a bell-shaped curve or the normal distributed curve or not? It's not. Okay. When your population distribution is not in a bell-shaped curve, even still if you are taking the sample size which is greater than 30, you can always eligible to approximate your distribution to a normal distribution. This is what we have learned based upon the central limit theorem. Okay, hence you can go ahead, okay, and you can, you know, the mean is same for the sampling distribution and the population distribution. The mean mu is equal to $64, whereas the sigma x bar is equal to 1.5. Okay, which we can clearly calculate it, and this is how the normal distribution that you have got based upon the mean value and the one standard deviation apart. Since the sample size is greater than 30, the sampling distribution can be approximated by a normal distribution. Okay, now you tell me, the heights of the fully grown white oak trees are normal distributed with a mean of 90 feet and the standard deviation 3.5 feet. Random samples of size 4 are drawn from this population and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Then sketch a graph of sampling distribution of the sample means. What is the population distribution represented over here? Is it a bell curve or a different curve? All of you? Yeah, it is clearly bell curve. Okay, it is a normally distributed. They themselves, the fellow has clearly mentioned it is a normally distributed. But even though it is normally distributed, the size of the sample is 4, which is less than 30. Now you tell me, when the size of sample is less than 4, I mean less than 30, which is 4, well, the sampling distribution will be a bell curve. Can it be approximated to normal standard normal distribution? Yes, we can. Yes, we can. How can you say no? That is what we learned earlier. Take a look at this one. If your population distribution is a normal population distribution, okay, then even though that your sample is lesser than, see, any n value means it may be 60 or it may be 6, then the resultant sample distribution will also be approximated to the normal distribution. This is what I told you, right? I don't understand why you see. I have clear cut. I have given you only two options. That's it. Very simple. Did you all understand or not still? Please let me know. I will re-explain. No issues. Here, the population itself is normally distributed. When you are taking the sample out of that population, obviously that will become normally distributed. Why you are worrying about it? Huh? Narayana, do you understand? You got it now. Okay. And someone told no. Who is that? Raju, are you good? Sanjeev, keep it up. I mean, do you have the same logic behind you are saying yes? Okay, fine. So now, can you please very fast give me the mean and standard error of the mean of the sampling distribution for the sale? Fast. Give me the answer. I'm waiting. Okay, Sanjeev already given me the answer. I'm waiting for the answers from some other. I will wait for a couple of more answers. That's it. Okay, I have got just only one more answer. Okay, out of you 10 people, 10, 11 people, I have got only 2 people answered. Okay, fine, I will go ahead. I'm expecting minimum 3 answers from out of 10 of you people, okay? Anytime, minimum 3, okay? So anyhow, let me just go ahead. Sunil Kumar, thank you. See, this is the right answer. Okay, if you are going to do a distribution, this is how you are going to get. Okay, and here you have one more example. Can you please identify this one very fastly? The graph shows the length of the time people spend driving each day. Look, there is an age group also. You randomly select 50 drivers age 15 to 19. This is the graph. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Okay, you have to you have to calculate the probability. Okay, you have to understand this is how that you can transform the x bar to a z score. Okay, this is the one which you can make use of. Is we are very much comfortable with the x minus mu divided by sigma formula. Okay, and here we are taking the sample and the x will become x bar, means it is going to be a mean, and sigma x bar will become sigma divided by root n. You will get the z score, and obviously you will identify the probability. I have given you the clear cut hint. Okay, so you can observe. Can you please tell me out of which, whatever that it is representing here, what is the standard deviation? It was clearly mentioned it is 1.5 minutes. Okay, and you can see the average time spent driving each day by age group. So based upon this requirement of this question, you randomly select 50 drivers age 15 to 19. What is the probability that they have asking? Okay, can you please tell me what is the mean value that you can take out of this particular diagram or this particular question? Hmm? Very good, very good. Mean is 25. Excellent. Okay, Raju and Sanjeev. Sanjeev, you are very active. I'm getting very first answer from you. Okay, so so you understood that this mean is 25. Hmm? Okay. See, mean is 25 and standard deviation I can immediately observe 1.5 divided by how many? 50 drivers I have taken. Hence, sigma divided by root n. Okay. When you see the sample size is greater than 30, right or wrong? Hmm? Okay. Now, what you have to do? You have to identify for 24.7 minutes and 25.5 minutes. Okay, this is one mean time and this is another mean time. This is x1 bar and this is x2 bar. Understand? You have to identify the jet scores for 24.7 and for 24.5. X minus mu divided by sigma divided by root n. Sigma divided by root n you have already calculated here. Okay, mu you have already have. X bar you already have 24.7 and 25.5. You will get two different values of jet scores. If you are going to make a subtraction between those two, you will get the resultant probability. Let me see who will give me the first answer. Please go ahead. And I'm expecting right answer rather than hurrying and giving me the first answer. I'm expecting the right answer. Okay, I will give you a couple of minutes. I will be right back. Meanwhile, please calculate and ping me the answer. I will just close. I will take a look at that. Let me see that some of you have got the answers, and okay, let me see. Even I don't want it to. I just want the final answer. Okay, look, this is how the numbers are. Okay, minus 1.41 and 2.36. Raju, very good, very good. And minus 1.1 and 2.36. Okay, good. Sunil, okay, you also good. Given the right answer. Narayana, right answer. Anusha, what is that value? I don't understand. Suresh, right answer. See, why are you not identifying those values directly from the jet distribution table, and you can finally give me the product and probability, right? Finally, what is the probability that we can have the people riding? I mean, 50 people who are riding in between the age group of 15 and 19. Okay, 91 percentage. I need this 91 percentage. I'm not asking you the jet scores. You have calculated the jet scores and given me. Okay, our main intention is to identify the probability. If you just open the jets distribution table right away there, you can identify those values and you can subtract and give it to me, right? Okay, anyhow, everyone given me the right answers. Okay, almost. Anusha, are you clear at least now? Are you good? You tried good, but I don't know what is the methodology that you have followed in order to get that answer. Now you are good. Okay, good, fine. So guys, we have one more. Okay, bank auditor claims that credit card balances are normally distributed with a mean of 2870 and a standard deviation of 900. What is the probability that a randomly selected credit card holder has a credit card balance less than 2500? Credit card balance less than 2500. Can you please immediately calculate the mean and standard deviation? Mean and standard deviation right away has given, and they have already told that they are normally distributed. Okay, randomly selected credit card holder means any one credit card holder that you are selecting, not a big issue. Why? Because you, even though if you take a sample out of them, definitely that should become normally distributed, no doubt about it. So in order to identify the probability, you can directly submit everything. You will get the judge score, which is going to be minus 0.41 and which is going to be the 34%. Okay, are you all with me? Are you good? Okay, Raju has a calculator and already given me. Good. So when you randomly select 25 credit card holders, which is less than 30, okay, which is less than 30, are we good that we can approximate to normal distribution or not? Guys, are we good to approximate the normal distribution? Huh? Yes, because the population itself is normally distributed. Okay, so you can calculate in the same thing vice versa. Okay, and you will get only 1%. Okay, 1% of the people you will get the okay, what is the you will get the 1% probability where they could maintain the minimum, I mean the less than the mean credit card balance less than $2,500. Okay, so this is what all thought I thought of discussing with you for the sampling distribution. Okay, and this is the summary of the problem that we have discussed just now. Okay, so what is the outcome of this one is there is 34% chance that an individual will have a balance less than 2500. There is only 2% chance that the mean of the sample of 25 will have a balance less than $2,500. It is possible that the sample is unusual, and it is possible that the auditor claimed that the mean is 2870 is incorrect. Why? Because here based upon this question, the second question, you randomly select 25 credit card holders. What is the probability that their mean credit card balance is less than 2500? We have already verified. Okay, but in the main problem, what it was mentioned is bank auditor claiming it. He's claiming that the credit card balances are normally distributed with a mean of 2870. So here, it is possible that the sample is unusual, or it is possible that the auditors claim that the mean is 2870, which is going to be incorrect. Okay. Why? Because there is only 2% chance that the mean of the sample of 25 will have a balance less than 2500. Not only that one, there is 34% chance that an individual will have balance less than 2500. From these two individual statements, we can clearly come to a conclusion that the auditor claim is definitely going to be incorrect. We can expect something like that. Okay, so anyhow, this is what all about the sampling distribution. Now tomorrow I will be discussing about the confidence intervals. Okay, confidence intervals. Okay, so new concept. So now we are almost into the inferential statistical stuff. Are you all understanding this part? You have to differentiate yourself what is descriptive statistics and what is inferential statistics. In the inferential statistics, we are trying to understand some conclusion out of it rather than just describing the data with some values. Okay, all of you? We will meet again tomorrow and we will explore the confidence intervals tomorrow. Okay, see you all tomorrow. Have a nice day. Thank you. Bye.